Is it? Okay, great. Hey guys, this is building a Kotlin Multi-platform advanced library. So we just had a great talk about using KMM, and in the previous to last slide, it was written contribute to the community. So this talk is about just that. My name is Salomon BRYS. I created Kotlin Coders, which is a European company dedicated to Kotlin Multi-platform. We were the first company to be certified by JetBrains for our Kotlin training. So if you do need training, please reach out to us. And the flip side of the Kotlin Coders company is actually the Kotlin framework, which is a set of high-level libraries that we are maintaining to help developers create easily Kotlin multi-platform mobile or non-mobile applications. And most of the libraries we maintain are targeted to every target the Kotlin compiler can compile to. And today I'm not going to be talking about a library of the Kotlin framework, but I am going to be talking about what we learned and how we did advanced stuff on our libraries. So I'm going to be using an example, which is cryptography, for this talk. The idea is not to explain what cryptography does or how it does it. It's just that it's a set of high-level advanced functions that are not available everywhere. And I want to show you how you can embed those functionalities into a Kotlin multi-platform library so that you can publish that library either internally or hopefully as an open source library to the community. So today I'm going to be talking about integrating 3 cryptography primitives into a Kotlin multi-platform cryptography library. So the first is SHA-256. It's very well known. It's a hash function, and it exists, and it is provided by the platform, by the Android platform in a Java or Kotlin API, and by the iOS platform in an Objective-C API. The second is SecP256K1, which is the ECDSA curve that Bitcoin uses, and it's provided by a native library. It's a C library provided by the Bitcoin authors, and so we are going to embed this functionality into our library by using JNI for Android and C-interop for iOS. So we are going to compile the library and embed it into our Kotlin multi-platform mobile library so that it can be used anywhere. And the last is CHA-20 Poly 1305, so it's an AEAD. It means, I don't remember, encryption with associated data, I think. And it's provided by the platform, but it's a relatively new algorithm, and it's optimized for our mobile processors. But the thing is, it only exists in Swift on iOS. It isn't provided as an Objective-C API. And as we'll see, this will be an issue when we want to provide a Kotlin multi-platform library with a CHA-Poly functionality. So the first stage is creating the library project. Each time you'll see that star, it means that I'm going to dazzle you with code. And so the abstract of this talk said that it was a live coding. It's a lie. I won't have time. I only have 40 minutes. So it's going to be a live review. So here I have my code. And here are all the stages that we are going to go through. And the first stage, the first stage is creating a multi-platform library. So I'm not going to go into a lot of details about that. The JetBrains documentation is pretty exhaustive. I just created a Kotlin multi-platform library that targets Android and iOS. I also turned on explicit API, which is also called library author mode, which forces me to write things correctly and not change the API without my users explicitly being aware. So it's pretty standard stuff, having the test dependency in the test implementation and configuring Android with the standard stuff. The only weird stuff is here. It just says that when you run test, notify me, because usually Gradle, the way Gradle works is when it runs test and everything goes right, it just it doesn't tell you that everything went right. So here I'm just explicitly asking Gradle to tell me. And so I have this SHA-256 implementation, and it's the actual implementation of SHA-256, and this is bad. Don't do this. Don't do this. Never use your own crypto. That's one of the first things you learn when you start using cryptography is never implement your own crypto, because you will make mistake, and those mistakes will cost you huge money, especially if you're working into the cryptocurrency business. Nevertheless, I did, and I wrote a simple test which tests the hash of hello world. Okay, let's run this. I'm going to run the check method, and then we'll see that the test just works. Okay. Okay, so let's say you believe me, because I don't have a lot of time. So it will compile in for iOS. So yeah, it just ran for iOS, and it will run for Kotlin. And yeah, this implementation of SHA-256 is correct, yet I shouldn't be using it. So what's the next stage? The next stage is to, oh, look at that. It actually ran fine. So what I'm going to do is preload the next stage. Yeah, here it is. I'm going to preload the next stage so that it is already compiled. Okay. So the next stage is to use platform APIs. So I'm going to use the platform API for SHA-256. And for that, I'm going to expect that a SHA-256 function exists. It will return me an interface, the SHA-256 interface. And then I'm going to implement it on Android and iOS. So that's pretty easy. You just have to expect a function in a common source code and actually implement that function in the Android and iOS code. So how do you do that for Android, for iOS? Because for Android, it's pretty straightforward. There's the digest API provided by the JVM, so I'm not going to go into that. How do you do that for iOS? So the nice thing is that Kotlin native already provides the entire Objective-C API for iOS in Kotlin native. So you have C and Objective-C APIs that you can use directly in Kotlin native. Here, for example, I'm allocating a SHA-256 context, then I'm initializing it, and then I'm getting the result. So here, what's interesting is that I'm pinning the input byte array. And pinning means that it will have a stable C pointer C pointer for this block. So here I can pass the address of the first byte of my byte array, and it will get filled. Of course, I still need to update so that I can hash a content. And here, instead of pinning the byte array, I can use ref2. Ref2 is the exact same semantic as pinning, the difference being that pinning is inside a block, ref2 only works within one simple function. And then later I need to free, of course, the context when I've used it. And Kotlin provides a nice function called memscoped that allows you, as you see, the native heap here disappears. So it allows you to forget to free objects, and it will free those objects for you. So as you can see, these SHA-256 init, update, and final are functions that are provided to iOS as an Objective-C API or a C API to iOS developers, and you can use them directly in Kotlin. So let's see how that looks. So now in my common code, I just have a digest interface and an expect function that says, okay, I expect SHA-256 to exist. If I go to the Android main source set, you can see that the implementation is that simple because it's basically the same API scope than the digest JVM API. So I just delegate everything to them. Like, okay, you want to update, let's digest.update. It's JVM API, it's pretty simple. On the iOS side, what's more interesting is that we are using the iOS Objective-C API directly in Kotlin, just like I've shown you. So I can call SHA-256 update, I can call SHA-256 final, I can reset, I can free the context, I can allocate it here, and all of that makes for a working SHA-256 implementation that uses the API provided by Objective-C, by iOS, without ever writing a line of Objective-C. So that's pretty powerful, and I ran the test just before starting. You can see that there's two success because Android runs the test twice, one for release, one for debug, and then it also works in iOS. So now we don't have our own crypto, everything runs fine, we can move on. And so now we want to use the SecP256K1 signing protocol, and that isn't provided by neither Android nor iOS. So we need to find a way to get these features. And the way that we do is by using this SecP256K1 C library. And so the first thing you need to do is to compile the C library for Android, which means that you need to target 4 targets, basically the 4 targets that are required by Android JNI, by the NDK. So this encompasses all Android devices and emulators. And you also need to compile for iOS, so 2 targets, and this presentation is a bit wrong because actually now you need 3 targets because you also need the ARM64 simulator target, which is the simulator for Mac M1. And what you can do also for iOS is build a universal static library, which basically means that you will build all targets and then embed all targets into one static libraries that will have binary code for every target. It's something that exists on iOS that don't exist on Android. And so the way you build a C library is hugely dependent on the C library. Some use autogen tools, so configure, make, and all that. Some use CMake. So I'm not going to tell you how to compile a C library, just that you need to. And once you've done that, then you probably need to configure Gradle, because what you want to have is a way to launch the app and compile all the apps. So because you're using Gradle to compile the multi-platform library, you need to create a task in Gradle. So here I create a task in Gradle that says, okay, run build ios.sh, and that it just will build the iOS library. But that's not complete. We need to define inputs and outputs. By defining inputs and outputs, we can tell Gradle, okay, check those inputs and check that those inputs haven't changed, and check that those outputs exist. If the inputs haven't changed and the outputs exist, then it won't recompile. And by defining inputs and outputs, you'll actually save a lot of times, because you will just compile the library once, and then every time you modify your Kotlin multi-platform library, you won't recompile the C library. So I greatly encourage you to take the time to define inputs and outputs for your compilation tasks. So let's see how it works. Oh, not a good one, okay. Let's get there. And so I'll immediately start the build task, which should appear here. Okay, so while it's building, I have the SecP256K1 entire source code, which is here. It's not mine, I've never touched it, and it's a C library with C files and C headers. And in my settings Gradle KTS, I've added SecP256K1. So now I have a project that's dedicated, a Gradle module dedicated to building these library. And now that I have that, I can write the task, the Gradle task, build SecP256K1 for iOS and build SecP256K1 for each Android target. So how do these shell script look? Well, for iOS, it's pretty simple because I'm using a script that I have found on the internet, which is called xconfigure. It's a script that will basically compile twice and create a universal library for iOS. So all I have to give it is the parameters that I'm giving it, that it would give to the SecP256K1 configure script, and then I basically move the file. For Android, it's a bit more complicated because I need to have the Android NDK location, the architecture I'm compiling for, the toolchain location, and all that, but it's all documented by the Android NDK, and in the end, autogen configure make clean make. So it's just a library compilation. In the end, you will get, not here, oh, it's still compiling. In the end, we will get one, oh, it's just done. So here we are, we have for iOS, we have the universal static library that was created, and it has both iOS targets, and for Android, we have a static library for each target. So once again, your mileage may vary. How you achieve this goal is entirely dependent on the C library that you are compiling, but in the end, you need that result. You need those four static libraries for Android, and you need either 1 or 3 static libraries for iOS. So I'll already, sorry, because it takes a while to compile, so I'm getting a little bit ahead. So now you need to embed this C library into a JNI code for Android. So how does it work? First, you need to write a Kotlin facade stating, okay, I will have all these native functions. Then you need to generate headers, and that's a pain because Java H is the tool that takes JVM bytecode and generates headers, and that tool has been deprecated in the JDK 10, so it's provided until JDK 9. So if you have JDK 11, which is the LTS release, then you don't have Java H. And how you generate headers, well, it's up to you. What I like to do is I extracted Java H from the JDK 9, and then I run it, and it still runs fine. But yeah, it still works until it won't. So one way or another, you need to generate those JNI headers. Then you need to write a C++ implementation, which means that you need to learn C++. Ouch. Okay, you can actually write this in C because the JNI works for C and C++, so it's up to you. And then you need to write a C make file for Android to compile your JNI implementation. And then you need to configure all that in Gradle. So JNI is a pain, and it's always been a pain. And, well, there's no way around that at the moment, so you need to do all that. So let's see how it looks. Okay, so first thing you need to do is tell Android, well, okay, now I have an external native build, so please read that cmakelist.txt. Okay, and so in that cmakelist.txt, where is it? It should be here. Okay, you're basically configuring the creation of your JNI static library, so embedding the SecP256K1 according to the Android API you are building for. But to write the C++ or C implementation, you need this header. So how do you generate this header? So as I've told, I have a Java H install on my PC, so it's quite simple. I have a task called generate JNI headers that depends on compile debug Kotlin Android because I need the bytecode, and once the bytecode is compiled, it's an exec task, so all I say is please run Java H, and I give it the class path and the class that it needs to generate header for. And as you can see, I also declare inputs and outputs, so it won't be rerun if nothing has changed, which is important. And now where is it? It should be here. Native headers, yeah. So the header that it generates is a C and C++ header, because there's this extern C if it's a C++ compilation, so it works for C and C++, and it gives you the list of functions of C or C++ function that you need to implement. And then you need to implement them in C or C++, and it's kind of a pain. It's straightforward, right? It's the same as with iOS when we were using Objective-C API. We need to pin you need to get the byte array element, which is basically pinning its memory, its pointer, and then we call the secp function, and then we check them, and if there was an error, we return null, and then we serialize to byte arrays by other secp256k1 function, and then we check, and etc. It's basically straightforward, but you know, it's C++, so by default, it's a pain. And then once you have all that, the Gradle configuration, the CMake list, everything, you can run the Gradle check. Oh, no, not check, sorry. Let's run test debug unit test. And it actually did nothing. Why did it do nothing? Because I forgot to remove this, which is what I want to show you. So let's do that one more time. And the test fails. Why does it fail? Because I've run the unit test on my machine, and I've compiled secp256k1 for Android, not for macOS. So, of course, it fails. It tries to load a static library that doesn't exist, that isn't compiled for macOS. So now you need to compile secp256k1 for macOS, and for Linux, if you have devs using Linux, and for Windows, don't do that. So the simplest way is just to say, okay, don't run Android unit test. So here I get all the tasks which are Android unit test, and I disable them. So now check will run, but you need to make sure that your CI runs connected check, either with an actual Android device installed or with an emulator running somewhere, and there, oh, it recompiles, it shouldn't. Well, so you'll have to trust me on that. It will actually run on the Android device, and it will correctly execute the code. Maybe, yeah. And then it will pass. So by having a JNI library, you now need either to compile it for all three major OSs on top of compiling for Android and iOS, or you can just disable the unit test for Android, and yeah, it started the unit test on my Pixel 5, and it ran. And so the unit test is basically, okay, I create a key, I get the public key for that key, I assert that the public key generated is correct, I sign the message, and I verify this. I sign a message with a secret key, and I verify that message with the public key. So that's Android. To be honest, JNI hasn't really evolved for a lot of time, so that's why it's such a pain. So now let's talk embedding that C library for iOS. And the first thing you need to do is write a C-interop definition file. It's a bit like the CMake file. What it says is, okay, I'm going to interop with this library, and I'm going to give you some information about that library. And then you need to write you need to configure Gradle so that it knows that you have a C-interop. And then you need to write a Kotlin facade. And what's amazing about that, it's a Kotlin facade. You don't need to write C or C++, just like with JNI. Basically, what C-interop will do is create a facade for you, and then you will use that facade to create your very own. So let's see how it looks. Okay, and so I'll run the check right now so that it will run while I'm talking. So first thing you need to do, as I said, is write your C-interop file. So what it says is, okay, I'm going to ask you to generate Kotlin functions for C functions that are in these headers. So now it's C, not C++. Kotlin native C-interop doesn't support C++ because C++ doesn't have a stable ABI. It's dependent on the compiler. So it's only C, and you give it the C headers, and you give it a filter stating, okay, because those headers will probably include other headers, and I want you to generate methods only for the headers that are in this file. And by the way, when you'll compile, you'll need to link against this library, and you can find this library in this folder. And you also need, because I'm using SecP256K1, these are the framework that SecP256K1 need. So once you have that, you run the C-interop Gradle task, and let's open, the iOS. And voila, you have the SecP256K1 function directly in your Kotlin source code. So that works. I forgot a step. You need, of course, to configure Gradle. Here in, where is it? Here, when you configure the iOS target in the Kotlin block, you need to say, okay, I have a C-interop called SecP256K1. So that's why it will look for the native interop, C-interop, SecP256K1 definition file. And you need to give it the location of the include file here. And of course, you need to say, okay, you need to compile SecP256K1 before you do anything, because if not, then you won't be able to link against the static library. But once you've done that, it's kind of magical, because you have all the SecP256K1 C functions that are available directly in Kotlin. And you can use the exact API that I've told you before. If you need to allocate something, you can call alloc, you can memscope, you can get the pointer, you can pin or use ref2 to pin a byte array. It's basically the same API that you're used to when you're using iOS API in Kotlin, but you added a bunch of function with C-interop. So it's way easier to use Kotlin native C-interop than it is to use JNI. And as you can see, the SecP256K1 test that I've shown you earlier also pass in iOS. So now let's talk about the last function that I wanted to show you, which is Chachapoly, which is this new algorithm that exists and is provided by the platform. So you already know how it works with Kotlin. You need to use the cipher JVM function that I provided. So let's see how it looks. Well, let's not, because you already know how it works. There's an expect function, there's an actual function, and the actual function just uses the cipher API provided by the JVM. It's boring, you know how to do that, and it's not the point of this talk. So let's assume that you understand how it works. The next stage is to do that for iOS. And the bad news is that Chachapoly only exists as a Swift API in the new CryptoKit framework provided by iOS. And CryptoKit doesn't have C functions, and it doesn't have Objective-C function. So it's only provided in Swift. And The bad news is that Kotlin only knows how to talk to Objective-C. You can't use Swift APIs in Kotlin. But fear not, Swift can actually interop really well with Objective-C. If it didn't, then Apple would have a huge problem. So, of course, they invested into making Swift interoperable with Objective-C. So what we need to do is to create a static library that will export the functions that we need in Objective-C. So how do we do that? Well, we need to create an Objective-C bridge. So now we need to write Swift, a Swift code. And what we need to do is create a Swift class and conform to that protocol. So we need everything that will be available to Kotlin to be available to Objective-C. And for that, we need the classes and function that will export to be annotated with @objc. And we need them to be public. And we need the classes to extend NSObject. If those three constraints are respected, then everything that's annotated with @objc will be available to Objective-C and by extension to Kotlin. Note that the function that we wrote in Swift are returning data results because we also need to create a type that will be exported to Objective-C with Kotlin, to Kotlin. By default, the CryptoKit functions in Swift don't return types that aren't exportable to Objective-C, so we also need to wrap the results. And then we create an Xcode project, a Swift static library. We write the Objective-C, Swift Objective-C facade that I've just shown you. We configure the bridging header, which is basically telling Xcode, hey, you need to create an Objective-C header that will contain all the declarations that we are exporting to Objective-C. And then we need to add the bridging header export logic because Xcode doesn't export that bridging header by default with the framework, so we need to add a small script. And then once we've done that, we can write a C-interop definition file. We can configure Gradle to use this C-interop. We can add the Gradle compilation task. We can configure Gradle to use this C-interop, and we can write a Gradle facade. Does that ring a bell? It should, because it's the exact same process that we did to interop with the C library SecP256K1. So once you have that facade, that static library in Swift, which exports Objective-C header, then the rest is just importing a native library, whether in C or Objective-C. It's the exact same process. So let's see how it works. Okay, so as usual, I'll immediately run the check so that it can compile while I'm talking. So, first of all, I'm going to launch Xcode and open the Swift Cha-Cha poly. So, I'm going, how does it work? Because it's not, oh. Okay, so you'll have to believe me. And you'll find that isn't there a way to, oh, yes. Okay, cool. So here we have the Swift Cha-Cha poly class. It's public, it's extending NSObject, and it has this @objc annotation, so it will be exported to Swift. Here we have the data result, which is the result class that I said we needed, and it follows the same protocol. It inherits from NSObject. It's public. It's annotated with @objc. Now, what's interesting here is that only the gather function are annotated with @objc. Did it succeed or did it fail? Objective-C doesn't need a way to create these objects, right? Because they will be created in our Swift facade. So these inits function are not annotated, and that's by design. And then we need to create a bridging header, and it's empty, but it needs to be there because it will be later populated by Xcode. And then in Xcode, in the build settings, so you aren't seeing this properly, but you need to tell here, you need to, in the configuration, you need to tell Xcode that there's a bridging header. And once you've done all that, you still need to add a custom run script. Because of this issue, the bridging header isn't exported by default with the framework that Xcode creates. So you need to add this run script to make sure that you are copying all the bridging headers. So once you've done that, you can create so the Xcode project is here, the code is here, and I added a build Gradle KTS file. So in my setting Gradle, I declared that I have a new module called Swift Cha-Cha Poly, and then in Gradle, I can use Xcode build, which is an exec task. So I can use Xcode build to tell Gradle how to build the Swift static library. So I don't have to build it with Xcode. I can use command line, and I can use Gradle. And as usual, I define inputs and outputs so that I'm sure that it won't run again if it isn't needed. And so the result of that will be a static library with Objective-C header. So once I have that, I can create my def file, and by default, C-interop interrupts with C, but it can operate on Objective-C. So all I have to do is tell, okay, I will operate on Objective-C, and then the rest is the same, right? You have headers, you have the static library, you have the static library path. Everything is the same as we've already seen. The only difference is this, iOS Simulator version min and iPhone OS version min. These are needed because Swift got a stable ABI from version 13, from iOS version 13. So actually everything that I've described to you doesn't work if you are not targeting iOS 12 or below. It only works if you are targeting iOS 13 and above. And once you've done that, you can use your facade and use the Cha-Cha Poly functions. Oh, sorry, yeah, this is iOS main. So you can use these function, where are they? Oh, yeah, they're here. So the nice thing is that now it's not C function, it's Objective-C classes that are exported. So we also have static functions. And those are functions that you can use just as C. So you need, for example, toData is a simple extension function that I wrote that pins the address of a byte array that creates an NS data for iOS and that moves data between these data and this byte array. So it's pretty much the same API that we've always seen. You've just added more classes and functions with these C-interop, and you created this static library to be interoperable with Objective-C. And yeah, I have this Cha-Cha Poly test. So I haven't shown you the test, but the way the test works is pretty much the same as every other test. I create a secret key, a nonce, I encode a text with an additional authenticated data. I verify that it is correctly encoded, and then I decrypt it, and I assert that the plaintext and the deciphered plaintext are the same. And so I haven't shown you the Android implementation, but it's boring. Yeah, we're simply using the Cypher API provided by the JVM with the Cha-Cha 20 Poly 1305 implementation provided by the JVM on Android. And now that we've done that, the last stage is to publish your library because application authors will need it. That's why you are creating it. So how do you publish your library? Well, it's actually quite simple. Where is it? It's here. All that changed was in the build Gradle KTS file. I added the Maven publish function, Maven publish Gradle plugin. And then I said that on Android, let's publish both all library variants, which means release and debug. And once you've done that, you will have access to the publishing Gradle task, and then it's up to you. You can publish to Maven local, you can publish to whatever Maven repository you want. Now, one thing that I need to mention is that here in iOS main, let's open secp. Here, I can access this function directly in iOS. And there's a bug actually in Kotlin Multi-platform mobile that makes it, that it won't work in the applications that depend on your project. And so right now it's called commonization, and commonization only works for the project, but not for the application that depend on your project. And it will eventually work, I think, in 1.6.20. And that's it for me. Thank you very much. There are two links here. The first is, of course, the demo project that I've used so that you can see on Git all the various stages and have fun with them. And this presentation is actually a web presentation. It's written with Jetpack Compose, and you can access all JetBrains Compose, sorry. It's a JetBrains Compose for web, and you can access this presentation and the slides and everything that's been said on that bottom link. And yeah, that's it. Thank you very much.